Hi friends, in this video we will see LC oscillator. So LC oscillator is also called as tuned oscillator. So this oscillator basically employs parallel LC circuit, and these oscillators generates sinusoidal wave only. So sinusoidal oscillations. These oscillations generally have some good frequency, so it is having high quality. So compared to high quality factor compared to RC oscillator, RC phase shift oscillator, compared to that it is having high quality factor, so which implies the frequency stability is also very good. So good frequency stability. So it generally uses parallel LC circuit. In this particular parallel LC circuit is also called as tuned circuit or tank circuit or resonant circuit. They're relatively very small. Actually they are using a very small reactor elements in the tank circuit. Okay, it's not that much big, but when compared to RC oscillator it is bulky only. Okay, because in RC oscillator there is no inductor at all, so when you include inductor definitely it will be bulky. So they are used to generate oscillations. Yeah, this part we see the oscillations can be in between 100 kilohertz to hundreds of maybe, and let me have 100 megahertz. So this is the oscillation range they can produce. So frequency range they can produce. And the main concept of this is based on the nature of reactive elements. We are having two different types of oscillators. One oscillator is called Colpitt's oscillator and second oscillator is called Hartley oscillator. So what is the diagram? So the diagram like this. We are having one amplifier here, op-amp, amplifier, and from this amplifier, see the single line diagram, so I can take single line from this diagram. So we are having X1 here, later X2 here, and finally X3 here. So here there are three different reactors. Okay, two different reactances are used. So this is connected to ground and this part is connected to amplifier like this. So these are three different reactive elements we are using. So now how to deal with it? Now we have two types of oscillators. One is Colpitt oscillator, Colpitt's oscillator, and second one is Hartley oscillator. So what Colpitt's oscillator do? So Colpitt oscillator gives X1, X2 and X3. So what are these elements? Based on these elements only we can define whether they are Colpitt's oscillator or Hartley oscillator. Coming to Colpitt oscillator, we are having capacitor here and inductor here. Coming to Hartley oscillator, we are having inductor here, capacitor here. So based on these elements only, elements of X1, X2 and X3, we can define Colpitt's oscillator or Hartley oscillator. Now let's move on to transistors Colpitt's oscillator. So here the diagram shows is op-amp based oscillator, but in the similar fashion we can go ahead with Colpitt's oscillator also. Okay, so I mean transistor based Colpitt's oscillator also. So here we will discuss only transistor based Colpitt's oscillator only. So how this will be? So this will be, yeah, this oscillator will be like this. First we have to take some VCC here. Through this VCC, one inductor is presenting. From this inductor, one capacitor. From this, another capacitor will be there. And okay, this is basically grounded. Okay, this is Colpitt's, what we can call, this is exactly the our LC oscillator. Yes, this is simple structure of LC oscillator, where we are having C1, C2 and L. We are having C1, C2 and L structure, so that's why this is called Colpitt's oscillator. Now to where we need to connect this? So we need to connect this to a transistor, and it is connected to a resistor, and it is grounded. So this is basic circuit. So now I am drawing remaining circuit like this. Again it is coming and connected to ground. Now this transistor is voltage divider type, so it will be like this. This is the structure of thing, and base will be fed back, coming to this, and it is shorted. So this will be from this inductor. Yeah, this will be shorted here and it is open here. That's all. Very simple concept. That's all. And from this, supply has been given. I mean, from this we can take voltage. Okay, so here the drawing of diagram is very easy. Okay, so this part, whatever this part is there, this part is the transistor's collector place. Okay, with this part is connected to transistor's collector, and this is the transistor, so it is in voltage divider thing. See, this construction is called voltage divider R1 and R2. So this is voltage divider biasing only, and this is RE and this is CE. Okay, these are stabilizing only. So this is RFC. So in between only these things will come. This is C1, this is C2, and this is L, and this will be our output. V0 can be taken from this. Okay, that's also. These are the things, and this point is called P, this point is called Q. And this is our simple transistor based Colpitt's oscillator. So what exactly happened to this means, it contains common emitter amplifier which introduces a phase shift of 180 degree. So this is called common emitter configuration. Yes, because of this we are getting a 180 degree phase shift. Okay, 180 degree phase shift. And resistors R1, R2 and RE are used to see this one and this one. This is CC and this one. So these three resistors are used to establish the desired operating point. So operating point can be defined based on these 3 points, R1, R2 and RE. So these three should be properly designed to get the proper operating point. And coming to the feedback network, it contains tapped capacitor and voltage divider, that is C1 C2 in parallel with the inductor L. So this is only the our tapped structure. Okay, C1 C2 and L. Okay, based on this the feedback network has been constructed. and the voltage across C1 has been taken, is fed back to the amplifier. See what exactly going on. This voltage is feeding back to the amplifier again through the coupling capacitor Cc. So this is the coupling capacitor Cc. Through this coupling capacitor Cc, the voltage across C1 is fed back to the transistor, and this is called RF choke. So the RF choke is a large inductor. So what is the requirement of this? It has two requirements. One is it acts as a DC short to power supply VCC. So for VCC is DC, so it acts as DC short. For example, I want to show right RFC advantages. First one is it acts as the DC short to VCC. That means from VCC the voltage current is coming through this RFC, not an issue, but it acts as an open circuit for AC. So it acts as a open circuit for AC. So no AC component is entering to VCC or coming from ACC. So this ensures that the top end of the tank circuit is not connected to the AC ground. Yes, so the top one is not connected to AC ground. So whatever is available there in terms of AC, that should be fed back to transistor. So due to split capacitor arrangement, so here the capacitor has been splitted like this, and due to this one, the tank circuit introduces 180-degree phase shift. So because of this type of arrangement, okay, it is producing 180-degree phase shift. So this is 180-degree phase shift for CE amplifier, and this is 180-degree phase shift for this splitted capacitor structure. So finally we are getting 360-degree phase shift. So hence I can use this circuit for an oscillator. So what happened? Hence the oscillators at point P and Q are 180-degree phase shift. So because of this reason only, as it is 180-degree, the point P and Q, they are in out of phase. That means 180-degree phase shift. So the total phase shift around the loop is 360 to it's over. So that's why what will happen? So it can be used as the oscillator. So what exactly happened with the output to the coupled things? Okay, the output is coupled to the load through a transformer. So through transformer it is coupled. You can see here. Transformer coupling has the following advantages. So why it is like this? So transformer coupling advantages. So what are these advantages? So it provides electrical isolation. So whenever transformer comes into picture, you can see it is providing electrical isolation, and it provides impedance matching between the oscillator output and the load. So it also provides impedance matching between output and load. Okay, so based on these two advantages, we are using transformer coupling at the output stage. Okay, so this is the explanation for transformer Colpitts oscillator. Then what is the frequency of it? So the frequency is also very simple. So the frequency is equal to 1 by 2 pi root L C equivalent. Okay, so what is C equivalent? They are in parallel, they are in series, C1 C2 by C1 plus C2. Okay, so this is the frequency. And what is the condition for sustainable oscillations? So the condition for sustainable oscillations is, the condition is HFE is greater than or equal to C2 by C1. So this is the condition. Okay, so these are the simple points we have to learn from Colpitt's oscillator. So the points are very simple. You can simply see common emitter amplifier, and so in collector side we just establish this type of oscillator such that two capacitors are splitted and it is in parallel with the inductor. And please give that feedback to again the transistor base through coupling capacitor CC. Okay, and you can see the coupling transformer also, and you have to know that why that coupling transformer is used. Okay, so this is the basic concept of Colpitt's oscillator. Now let's move on to the Hartley oscillator. Yes, so here transistor oscillator will be there. So how to draw this? So this is also very simple concept. You can see I am drawing from VCC. Okay, I'm drawing from VCC, and this is my RFC. Okay, RF choke, and tank circuit will be here. Let me leave the tank circuit, some space for tank circuit, so that I want to show the equality from the previous circuit. Yeah, so this is the simple transformer bias. Okay, voltage divider bias. So it is with resistor here, and it is also with one more resistor. It's connected to this part, and similarly this part is connected to capacitor CE. Okay, and this is like this, and what more? That's all. This is the basic structure. Now here we need to I want to provide capacitor here, and it should be in parallel with the inductors. Two inductors should be separated here. So I have taken from here, this is L1 and this is L2, and this is going to CC. Okay, this is CL, and here it will be output. So this is the concept, and this is the tank circuit now, and VCC. These things we will see, and it is not connected like this. So here it will be. That's all. So here we can see so this is common emitter configuration of the transistor in its voltage divider bias. So you can see this is VCC, and it is connected to R1, R2, and this is the transistor. So in between RF choke, in between RF choke and this collector, there is a tank circuit, capacitor divided, and inductor is divided into two parts. Okay, from this second inductor we are taking the output voltage, and middle one, the midpoint of these two inductors is connected to ground through CL. So this is the concept, and in this way it is having CC is the coupling capacitor. Same thing what we have seen in the Colpitt's oscillator. Now let us quickly see what the speciality in this Hartley oscillator. So the feedback network contains a tapped inductor, voltage divider L1 and L2. So this part he has explained. So it is in parallel with the capacitor. L1 is fed back to the voltage across L1. Now voltage across L1 is feeding back to transistor through coupling capacitor. So again it shows RF choke is a large inductor. So this part we have already seen. Then it serves two things. First thing is the DC short, and second one is the open circuit. So the purpose of RFC is, first one is it is for DC, it is short circuit, and second one is for AC, it is open circuit. Okay. CL is providing the ground for this two L1 and L2. So what happened, due to the split inductor arrangement, the tank circuit, because of this, Okay, this tank circuit will produce 180-degree phase shift. Okay, now same thing as like Colpitts only. This is providing 180 degree, and this inductor splitting provide 180 degree, so finally it will be 360 degree. And what is this coupling transformer? So the coupling transformer gives us, okay, we have seen already, the coupling transformer gives us again two advantages. First advantage is isolation, electric isolation, and the second one is it provides impedance matching. Then what will be the frequency? So the frequency will be equal to 1 by 2 pi root L equivalent into C, because L is doubled here. So what about L? L equivalent is equal to L1 plus L2 plus 2M, where M is the mutual inductance. Then what is the condition for sustainable operation? So the condition for sustainable operation is, sustainable oscillations is HFE is greater than or equal to L1 plus M divided by L2 plus M. Okay, if you feel that mutual inductance is very less, then we can remove that. HFE is greater than or equal to L1 by L2. Okay, so this is the main concept in Hartley oscillator. So in this LC oscillator, based upon the elements, we are having two types of oscillators. One is Colpitts oscillator and second one is Hartley oscillator. So based on the arrangement, we have to proceed. So thank you for your careful listening, and please like this video, share this video, and kindly subscribe to my YouTube channel. Thank you so much.